All right, welcome to ECE203. What we're going to be covering in this video is the remainder of Lecture 4 and also the remainder of Lecture 5. Now in Lecture 4, where we ended off is building up some of the basic building blocks in CMOS and paying particular attention to building these building blocks in operating in subthresholds. So we analyze common source amplifiers, source followers, etc. And then we introduce the concept of a differential pair. And that's exactly where we're going to start off today, is talking about differential pairs. Okay, so as we said in the last class, a differential pair looks something like this. We have some set of, in this case, NMOS transistors, although we could have built these out of PMOS transistors. It's really up to us, that are biased by some current source, I bias. Okay, and so at the input of these two transistors, we have two voltages, and let me make sure that that is in the IEEE convention. That is the DC plus AC voltage, so we'll use lowercase for the variable name and uppercase for the subscript. Let's call this transistor M1, that transistor M2, and we have some current I1 and I2 flowing through these devices. And these devices will be connected to some active circuits on the top. We're not going to concern ourselves too much with what's going on up there. We really want to analyze the input voltage to output current transfer function. Let's call this interior node here Vx. Okay, so what we can say then is that if I bias is small, if I bias is small, then M1 and M2 are going to be in subthreshold. Now, how small is small? Well, that depends on the size of the transistors and so on and so forth. But let's assume that they are in subthreshold, and further, let's assume that within the subthreshold domain they are saturated. And what that means is that VDS is larger than roughly 100 millivolts at room temperature. And further, let's ignore, for the purposes of this analysis, let's ignore the body effect, and let's also ignore Dibble. Okay, so if we do that, then what we say is that I out, and this is the large signal approximation, is going to be equal to I1 minus I2. We're just taking a look at the differential version of I out. That's going to be equal to I off. We're assuming that M1 and M2 are sized roughly the same, so that I off is the same between them, times E to the Vin1 minus Vx. That's the drain to source, or sorry, gate to source voltage across that first transistor over N phi t, minus I off of M2, which we're assuming to be the same as M1, minus Vin2 minus Vx over N phi t. Okay, so that describes the output current of our circuit. So then what we can do in the next step in this analysis is I'll say, well, let's take I1 divided by I2 for reasons that will become clear shortly. And if we divide these two, we get the following expression. The I-offs cancel out. We get E to the Vin, and let me make sure that I'm again using my IEEE convention, Vn1 minus Vn2 over N phi t. All right, so then what I'm going to do is I'm going to take I1 over I1 plus I2 for reasons that will again be clear shortly. And what that really means is that that's I1 over I bias. Right, this is the large signal model. I bias sums out through KCL to the current going through both M1 and M2. Okay, so what we can do here is that we have the ratio of I1 to I2, so we can substitute in I1 for I2, and what that gives us is I2 times E to the Vn1 minus Vn2 all over N phi t, divided by I2 times E to the yada 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 plus I2. Okay, so in other words, I'm saying I'm going to actually write down the first expression that I had here, I1 plus I2, on the bottom here, and I'm just doing shorthand for those I's. And what we see here is that these all cancel out, and we're left with a ratio of exponentials. So what we can say then is that I1 is equal to I bias divided by 1 plus e to the Vin1 minus Vin2 over n phi t. Okay. Now similarly, we can do a similar expression for I2 that's equal to I bias over 1 plus e to the, and I apologize, hold on, that should be minus Vn1 minus Vn2, and in this case it's e to the plus Vn1 minus Vn2 over n phi t. Okay, so then what we can say is now we have expressions for I1 and I2. So what we can do is we can go ahead and find the differential output current, that's ID out. And that's going to be equal to I1 minus I2. And that's equal to I bias. And we just basically subtract these terms. And what you're going to find out that it's 1 over 1 plus e to the minus x, where x is this Vn1 minus Vn2 over n phi t, minus 1 over 1 plus e to the plus x. And that's the expression for I. And k is again equal to Vn1 minus Vn2 over n phi t. Okay, so this should start to look to like something like a somewhat similar expression here. So what we're going to do to simplify is we're going to multiply this branch here. We're going to multiply by e to the plus x over e to the plus x. So we're going to multiply by 1. And if we go ahead and we do that, we get the following expression. We get I bias. And now on the bottom here, we're 1 plus e to the x. But of course, now we have our term in the numerator here. And so what I'm going to say here then is that I bias is now equal to e to the x minus 1 over e to the x plus 1. All right. And then if we go ahead and substitute in for what we get with this trigonomic expression here, is we recognize that this is actually representative of the tanh function. So we say that this is equal to I bias times tanh of Vn1 minus Vn2 over 2 n phi t. All right, let's go ahead and box that answer here. All right, so this is very cool. It's very interesting. This is first of all, this is the large signal model. So we didn't take any approximation. We're not doing any linear approximation to the circuit. We're getting this tanh function, and that is the large signal model. So what we can go ahead and we can do is we can say, well, let's actually draw the plot of what this looks like. And this should look very similar to what we plotted in the last lecture, except this time what I'm going to do is I'm going to plot it. I'm going to plot I out. Let's make that lowercase here. IEEE convention, I out versus V in 1 minus V in 2. Okay, if we go ahead and we do that, we get a plot, a function that looks something like this, like a tanh function. Okay, and it goes between minus I bias to I bias and cuts right through the center at 0. Okay, so what we'd like to do now is, this is the large signal model, so this perfectly describes our entire system. So what we'd like to do now is we'd actually like to try and linearize this. And so we want to linearize here in order to create a small signal model. Okay. So that's exactly what we're going to do. Now, one note we can make with the circuit is, interestingly, this is a circuit that is very suitable for both analog, in other words, kind of linear processing of information, if we restrict the range of input voltages to be somewhat narrow, and we'll actually define what that exactly means a little bit later on. Or we could operate this circuit as a digital circuit. If we assume Vn1 minus Vn2 swings large, then we get this very digital switching between our output nodes. Okay, so this expression here, this I bias times the tanh function of Vn1 minus Vn2 over 2n phi t, is a nice, beautiful expression that perfectly, well, not perfectly, but that well describes the relationship between the input current, or between the input voltage and the output current. Now, if we compare this, for example, to above threshold, if we compare to above Vt, what we get is that ID out, and I'm not going to do the derivation here, but I'm just going to write down the answer, is equal to I bias times Vn1 minus Vn2 all over VOV, that's the overdrive voltage, VGS minus VT, times the square root of 1 minus Vn1 minus Vn2 over 2 VOV all squared. Okay, so it's kind of a nasty expression, and just for clarity, VOV is equal to VGS minus VT when, and this is important, when Vn1 is equal to Vn2. Okay. So this is a little bit of a more nasty expression. If we want to linearize this, it'll take us a little bit more work to do that in a nice way. However, linearizing the transfer function with the tanh, as we'll see, is actually going to be pretty easy. Okay, so we're going to get back to this topic momentarily. What I'd like to take a little bit of a detour and talk about are current mirrors. Okay, so current mirrors are devices that we're going to use to bias all of our analog circuits, and they have several requirements. These requirements are as follows. They should output a constant current, ideally, independent of process, voltage, and temperature variation, and they should also have a high output resistance. And it turns out that achieving both of these goals is extremely difficult. There's a lot of literature on building band gap references and other type of low power current references, including some research going on in my own research group. But generally, we only like to do this once, and so generally what we say is that it's much easier to copy what we call a known good current somewhere else on the chip. So instead of having to design a current for every single block that we're trying to bias, let's just spend a lot of effort and design one known good reference. So this will be some sort of temperature compensated, some sort of temperature compensated current reference, which we're not going to have the opportunity to discuss in this class. If you're interested in reading more about it, there's lots of papers and textbooks and literature on doing band gap references and other type of current reference circuits. Okay, so in other words, what we're going to focus on in this class is, let's just say that someone has done a good job and designed a nice IREF, some nice DC current. What we're going to do is we're going to build a device called a current mirror that can go ahead and then take this current and copy it over to other circuits, other blocks in our system. And we can do this a bunch of times if we need to. Okay, so this is what we are going to call our current mirrors. Now, we can also get very complicated with our current mirrors. Let's take a look at the basic current mirror. And this basically will complete the discussion of basic building blocks in this class, as we'll go ahead and continue our discussions on differential amplifiers. But for the moment, let's just take this very basic structure. We have some sort of reference current that's being supplied from somewhere, IREF. And what we're going to do is we're going to put that into an NMOS transistor. Again, we could use PMOS here. It depends on the application. And then we're going to mirror that over to another transistor, another NMOS transistor. And specifically this transistor here we're going to set to be diode connected. And this node is, say, Vx. And this is what we're going to describe as our output current. Now let's say this is device M1. It has a W over L ratio of 1. This has a W over L ratio of 2 because it's device 2. Now in subthreshold, so most of you have analyzed this circuit in above threshold. Let's analyze it in subthreshold, see if it does the same thing. So in subthreshold, Iref is equal to I off 1 times e to the Vx over n phi t. I out is equal to I off 2 times e to the Vx over n phi t. Okay, so you can see here that if I off 1 is equal to I off 2, then I out is going to be equal to I ref. Okay, so very good. We've done the job. This is a nice basic current mirror. Now, of course, we're making a lot of assumptions here. This is ignoring Dibble. It's ignoring channel length modulation, etc. Okay, but to a first order, this is correct. Now, what's nice about this kind of structure is just like in above threshold, if W over L2 is equal to M W over L1, in other words, the output current source is M times larger, then we get an M times multiplication. In other words, I out is equal to M times I ref. Okay, so life is good. This is a current multiplier. Okay, so in other words, current mirror designs in subthreshold are essentially the same as they are in above threshold. Now the design is a little bit relaxed because we don't require as much VDS to keep these devices both in saturation, but essentially the basic principles of current mirror design apply equally well into subthreshold. And in addition, we can apply the same type of tricks. We can do cascoding to help improve the output impedance and things like this. Okay, so before getting back to our topic of differential amplifiers, I'd like to do one more sidestep on something we call TransLinear Analysis. Okay, so this is kind of a neat form of circuit analysis that you might find useful. If you want to read more about it, you can take a look at chapter 14 in the Sarpeshkar book. Okay, so what we're going to do here is we are going to leverage exponentials in sub-threshold CMOS together with the following expressions that turn out to be very useful. So these following expressions are just mathematical identities. We say log AB is equal to the log of A plus the log of B, and similarly log A over B is equal to log A minus log B. Okay, so we're going to use this in the analysis of the following circuit. So let's consider a Kirchhoff voltage loop. Operating a subthreshold, so therefore we have the exponential IV characteristic that we're looking for. Okay, so let's just say we have two sets of differential pairs. Okay, so let's say we have two NMOS devices here, and they come together to present some differential pair, and let's say this is biased with a current I1. Okay, and let's say that this differential pair is connected to another differential pair. Who looks like follows. All right, and this differential pair is going to be biased by I2. Okay, now let's start labeling a few of these nodes here. Let's call this V in 1. This here is V in 2. And furthermore, let's assume that this is connected to the same voltage here. Okay, so Vn2 is connected to both this side and this side of the FET. Okay, now let's make a few more labels. We'll call this current I2x. We'll call this current I1x, and this is the current going in this direction here. And this current here, I1y, and this current is I2y. Okay, so I think we have all of our labels with the exception of nodes X and Y here, which should complete the description of the circuit. Okay, so what we'd like to do is we notice that actually this input actually forms a loop here. So we have Vn2 goes across here. We have a VGS drop to node Y here. We have a VSG drop to Vn1, Vn1 VGS to node X, VSG to node Vn2. Okay, so that's a Kirchhoff voltage loop. So let's go ahead and write down the expression for that Kirchhoff voltage loop. That's Vn2 comma X for the X transistor plus Vx in 1 plus V in 1y plus Vy in 2 is equal to 0. Okay, so what this is basically saying is we're saying V in 2 to node X plus Vx to node V in 1 plus V in 1 to node Y plus Vy to node V in 2 complete a Kirchhoff voltage loop. Okay, so we can go ahead and rewrite this expression. That's V in 2 comma X plus V in 1 comma Y is equal to V in 1 comma X plus V in 2 comma Y. Okay, so I've just kind of rearranged the negatives here to make this a little bit better. So let's just recall one thing before proceeding to the next step, and what this is I2x is equal to I off, and this is specifically referring to the current in this first NMOS transistor here. It's going to be equal to I off times E to the V in 2 comma X over n phi t. Okay, so what we can actually do is we can rearrange. We can solve for V in 2 comma X, and that's going to be equal to n phi t times the natural log of I2y over I off. All right, so what we can then do is we can go ahead and take this V in 2 comma X and substitute it into this expression up here, and we can similarly do so for all of the other V in and X's. Okay, so what this does is all of the n phi t's will cancel out, and we'll be left with an expression that looks as follows. We say the natural log of I2x over I off plus the natural log of I1y over I off. Also noting that the x's are part of this expression is equal to natural log of I1x over I off plus the natural log of I2y over I off. Okay, so obviously all of these I offs cancel out, and in fact also all of the natural logs cancel out, and we get the following expression. We get I2x times I1y is equal to I1x times I2y. Okay, so why is this significant? Well, what we've done is in the prior section when we were discussing current mirrors, we found a way that we could multiply currents by fixed coefficients whose coefficient is set by the width of a gate. Okay, in this situation, we found a way to multiply two separate variables. So in the first case, we're multiplying some current, which could be a variable, by a fixed coefficient. In this case, we found a way to actually multiply two different currents. Okay, and so what's really interesting is we went from a sum of voltages, and the sum of voltages turns out to equal a product of currents. Okay, so in KVL analysis, sums of voltages are equal to products of currents. So that's really neat, actually. And we could just summarize this. Sum of voltages is equal to the product of currents. Okay, so that's kind of the a nice, cool thing that is very useful in the context of, let's say we have some analog signal that we're trying to capture, and we'd like to do a little bit of pre-processing of that analog signal. Well, what this translinear type of circuit allows us to do is it allows us to do some amount of analog processing. We can do multiplication, we can do addition by basically just summing current nodes together. We can multiply by fixed coefficients. So you can imagine you can build some sort of basic analog computer using the techniques shown here. And because we've introduced this translinear analysis, it's actually very simple to come up with some expressions to do some slightly more complicated math. So if you're interested in using this for something like some analog pre-processing of your signal, this is a useful tool to help you get up to speed with your analysis techniques. So let's get back to talking about the differential amplifiers that we're interested in analyzing a little bit more. They're going to play a very important role for us in this class as we deal with amplifying biopotential signals. So let's take a look at a differential amplifier with a differential output. Okay, so what does this circuit look like? Well, we have our differential pair that form the core of the amplifier as we analyzed before, but in this case we're actually going to build it as a full amplifier here. In this case I'm not going to say that we have this ideal current source, but we're actually going to bias it with some transistor that has some V bias applied to its gate and some which generates some current bias at its drain. Then we have our differential input pair. In this case, we're going to use our differential signaling terminology here. We have our common mode input plus our differential mode input. On this side, we have a common mode minus our differential mode input over 2. And then what we're going to do is we are going to resistively load this particular amplifier with some load resistance RL. And what we're going to do is we're going to take our output voltage differentially. Okay, so we're going to take our output voltage like this, and we're going to call this V out. All right, now one more note, this is M1, this is current I1, this is M2, this is current, as you may have guessed, I2. Okay, so what we can first say about this circuit is that at AC, node Vx that we're labeling here, Vx is what we consider to be a virtual ground. And so what this means is that if this is truly working as a differential amplifier, then if we apply a differential input signal, then node Vx is not going to change in potential provided that this circuit is well matched. And so what that implies to us for a circuit analysis is that we can break the circuit into two half circuits. Okay, the circuit of which will look something like this. We just have our resistive load RL. We have our transistor here. This is VID over 2, and this is V out. Okay, now the small signal version of V out, let me just label it as in the IEEE convention with lowercase letters, is just going to be minus GM VID over 2 times RL. As we would expect with a normal common source amplifier. So then what we can say is that that's the output of, say, one of those amplifiers. So the actual differential output voltage, V out, is going to be V out plus minus V out minus, which is equal to GM VID over 2 RL minus GM VID over 2 RL, which is equal to GM VID RL. Okay, and so basically what this means is that the differential mode gain, and I'll abbreviate this AV, DM, is just GM RL. And, you know, interestingly enough, that's exactly the same as our common source amplifier. And of course, those of you who've taken circuits classes before are not surprised by this result. So what I'd like to do now is take a look at a differential amp. But this time, with, I'm sorry, that's a very poor A, let me try again, amplifier, but this time with a single ended output. Okay, and so what we're going to do in this amplifier is we're going to again start out with our usual differential pair forming the base of our circuit as follows. Again, we're going to bias it with some actual NMOS transistor here, V bias, I bias, okay. And these input signals are going to be the same, VCM plus VID over 2, VCM minus VID over 2. But in this case, we're going to replace our loads, those resistors rather, with some sort of active load. Okay, so we'll replace it with some sort of PMOS device and some sort of PMOS device up here. And specifically, we're going to create this active load in the form of a current mirror as follows. Okay, and we're going to take our output voltage here. This will be called V out. All right, so let's label a few things. This is transistor M1, M2. Let me label some currents. This is I1, this is I2, and this here is I out. Now, this is a current mirror. So as a result, the current flowing through this branch, if these transistors are sized to be the same, which they nominally are, so this is M3, this is M4, these transistors should nominally have the same current in them if they're sized to be the same device, even at small signal. And so therefore, this is a mirrored current I1. And so what we can say then is that the differential I out current is going to be equal to I1 minus I2. So that's exactly the same as before. So the same kind of tanh function applies here. Now, what is interesting about this circuit is that this is not a symmetric circuit. Okay, this is not a symmetric circuit. So what this means is you cannot use half-circuit analysis. And so that really made the process very easy on the above circuit. We were very easily able to find the small circuit gain, or the small signal gain. In this case, we can't do that. And so it turns out that you can draw small signal models for all of these transistors. You can do some analysis. It gets a little complicated, particularly if you want to include RO and things like this. But I'm going to show you perhaps a slightly easier way to do this when this circuit is biased in subthreshold. So a different way to do this is to find gain. What I'd like to do is first find the overall transconductance of the circuit, then find R out, or the overall output impedance of the circuit, and then what we can say is that the differential mode gain is going to be the overall transconductance of the circuit multiplied by the overall output resistance of the circuit. So then we can recall that in subthreshold, I out, and this is the large signal behavior, is I bias times the tanh of VID over 2n phi t. Now this was the large signal circuit. Let me just make a note here. This is large signal. And this exact equation actually applies to this circuit because I out is equal to I1 minus I2, which is exactly the same situation we were dealing with earlier, even though we didn't consider what this active load was actually supposed to be. Okay, so then what we can say is that we know I out, so what we can do is we can derive what the overall transconductance of the circuit is simply by taking the derivative of I out with respect to the input differential voltage. Now if we take the derivative of the tanh function, what do we get? We get I bias over 2n phi t times 1 over cosh squared of VID over 2n phi t. Okay, so that's the derivative of the tanh function. So what does this look like? Well, let's just refamiliarize ourselves with the transfer function that we had originally derived. This is our input differential voltage. This is our output voltage. And remember, it looked something like this. It was some sort of tanh function. And it peaked out at I bias. And on the downside, it peaked out at minus I bias. And what we were interested in looking at is the slope of this circuit, okay? And that is what we consider to be the small signal slope. Now, when we take a look at this circuit, one thing that we can say about this is what would be, say, let's say the effective linear range of the circuit. Well, one thing that we can say is, if we were to say extrapolate this linear component of the circuit, you can only go as far as the rails. Now, of course, you're not going to get exactly that because there is some compressive nature to this circuit, but to a first order approximation, you could say that perhaps a box that would surround this extrapolated small signal model to be the linear range of the amplifier. Okay, and so what this implies then is that the linear range is going to be fairly small depending on what the slope of this line is. So this was the actual tanh function. What we did to get the GM is we took the derivative. So we took the derivative with respect to VID, and what that got us was this 1 over cosh squared function. Now it turns out the 1 over cosh squared function looks something like this. All right, this is this is what the cosh of x function looks like, and it turns out that for x equals to 0, cosh of x is equal to 1. Okay, so what that implies here is that 1 over the reciprocal of 1 squared is just 1, and so what we can say is for small differential input voltages, we can say that the transconductance of the overall circuit is equal to, is approximately equal to, basically we can remove this first part of the term here and we get I bias over 2 n phi t. Okay. Now it turns out that this looks very much like the transconductance of a single MOSFET device, perhaps divided by 2. But actually, we see some sort of current divided by 2 and then n phi t. It turns out that I bias divided by 2 is exactly the current that flows through one of these devices for a actual differential circuit implementation for small differential input voltages. So what we can say here is that this is also equal to I1 divided by n phi t, which is just the normal transconductance of our regular device here. So after all that analysis, the end result is that the transconductance of our single-ended output differential amplifier is just the transconductance of our original device. Okay. So what I'd like to do now is just formalize a little bit that discussion we had on linear range. Let's just talk about that for a few moments here. We're going to define it here, at least, as the intercept of the GM slope at VID is equal to 0 with the saturated current. In this case, I bias. Okay. So what we can say then is that in this example, GM times the linear range is going to be equal to I bias. That's the intercept point. So then we can substitute in what GM is. That's I bias over 2 n phi t times the linear range voltage. That's equal to I bias. And what this implies then is that the linear range of our amplifier, VLR, is equal to 2n phi t. for this particular example, for a subthreshold differential amplifier with single-ended output. Now we know what N is, we know what phi t is, at least at room temperature, we know what the factor 2 is. That's roughly equal to 72 millivolts. Okay, so you might be thinking, that's not great. And you would be right, depending on the application, I suppose. But that may not be a huge amount of linear range. If you're expecting your input signals to be larger than the 72 millivolts, then you are not going to be amplifying them linearly. And furthermore, if you consider that, well, actually this is a little bit of an approximation, you know, we do get some compressive behavior here as we asymptotically approach these I bias and minus I bias current ranges. So this is actually perhaps even not quite a very good approximation, and our linear range is actually a little bit worse than this. So that may be a problem. We're going to propose a few ways to address this momentarily. But I wanted to talk about one quick aside. And this says that the linear range in above threshold differential amplifier is roughly equal to VOV, or the overdrive voltage. So this can potentially be larger. So the downside about the subthreshold implementation is the linear range is 2n phi t. You as the designer have no control over 2n phi t other than perhaps through some strange way some temperature parameters here. So you have very little control. We have to invoke different type of circuit architectures in order to actually build a circuit like this. Okay, so in above threshold we don't have that problem. We can choose VOV depending on our mode of operation, how much voltage headroom and stuff that we have. So we do have some potentially larger linear range. However, this comes at the cost of less power efficiency, because we're operating in above threshold, and 2, less common mode DC operating range, and larger VDD min, the minimum supply voltage that we can work at, just because of the need to overdrive our transistors. Okay, so let's go ahead and discuss ways to improve linear range. Okay. All right. There we go. So basically what we're saying here is that in subthreshold, the linear range is defined as it's proportional to some transconductance and to our I bias current. So essentially the most straightforward way to increase our linear range is to lower GM. We can do that in a number of ways. We can perhaps by, instead of using the gate input, we could use the back gate. We know that GMB is n minus 1. So in other words, using GMB instead of GM. So we know GMB is a little bit worse than GM, so perhaps that's one way to improve the linear range. Another way is to use something, a technique we call source degeneration. And essentially what we do here is, let's say this is the input of our differential amplifier. What we'd like to do is add some sort of degeneration resistor here. And in fact, let's actually go ahead and drive this input from the back gate in order to make use of the above point here. And so essentially what ends up happening is we establish some sort of negative feedback that causes less current per unit of input voltage change. And that's exactly akin to actually reducing the GM. So to understand how this works, it doesn't look like there's feedback going on here, but let's just take a look at an example. Let's say that Vn goes up. Okay. What that means is that ideally the current in the circuit should go up. However, the current in the circuit means that there's a larger current flowing through this resistor here, which means that it's going to have a larger IR drop. Okay, and because it has a larger IR drop, that's going to cause the source voltage to go up. The gate voltage, it's just biased to the output voltage. It has no bearing, or not a huge bearing on this, is relatively constant, which means that VGS goes down, which implies that the current goes down. So you can see that there's kind of this negative feedback loop going on here that causes our effective transconductance of this circuit to decrease. Another way to do this is to use a different technique that's a little less popular called gate degeneration. Okay, so let's imagine that we have a, let's actually transition to a PMOS input for the purposes of this example. So this is our PMOS device. Let's say we apply some sort of source degeneration to it as well. Again, this is a PMOS, so I'm going to use a source degenerated voltage or some sort of source degenerated active transistor instead of a resistor. So you can think of this as kind of some sort of diode that's acting as some sort of resistance. So let's say this is our input signal here. This is Vin plus. And then what we're going to do is something, a technique we call gate degeneration. So remember, this is the drain of the PMOS device here, because source and drain are swapped, and this is going to go to some other transistor here. We're basically going to mirror this circuit here, okay? And we're going to actually connect this PMOS transistor in a diode connected way, okay? So this also operates, and this here is what we call the gate degeneration transistor. So this also operates using negative feedback. So to understand how this is working, let's take a look at our Vin plus signal. Let's say it goes down. So we're going to look at PMOS. So going down means current should ideally go up. Okay, so current should ideally go up. However, what happens here is that, let me annotate this node here. This is VSG of the input transistor. What happens is that when current goes up, this is VGD of the transistor, because the gate and the drain are connected together. The gate and the drain are connected together. This is what we call VGD. Okay, so what ends up happening is that when current goes up, that implies that VGD also goes up, which then implies that VSG in, this is the source to gate voltage of our device here, has to go down, which then implies that current must also go down. So it's this similar type of feedback structure that's working here to further degenerate the current. And then what we do is we just mirror it out here to some sort of a current mirror that we can use in some other circuit. Okay. Now there's another technique that we could describe. It's called bump linearization. I'm not going to get into the detail here. If you want to read more about this and the other two techniques that we discussed earlier, I would recommend that you take a look at section 12.2 in the book for more information. Okay, so that was a little bit of an aside. Let's get back to our calculations about gain. Okay. Okay, so this was a little bit of an aside about linear operating range. What we were trying to do originally is we're trying to find the gain, right? We're trying to say if we could calculate the overall transconductance and then the overall output resistance, we would have the small signal gain without having to do all the small signal circuit model analysis. And we found that GM is equal to I bias over 2 n phi t times 1 over cosh squared. We found that 1 over cosh squared was roughly equal to 1, and therefore the transconductance of our circuit was essentially just equal to the transconductance of a single one of these transistors. Okay, so for our out, what we need to do is we need to apply a test voltage. We calculate R out in the usual way. We apply a test voltage source when we short the other sources in the circuit to 0 and find the resulting current. Well, it turns out we can go ahead and do that. I'm going to skip the steps. It turns out that it's a fairly simple expression. R out is basically equal to RO2 in parallel with RO4. That's just the output resistances of our circuits, of our two transistors there. Okay, so therefore what this says is AV differential mode gain is equal to GM times RO2 parallel RO4. That's it. Okay, which is roughly equal to GM R0 over 2. That's if RO2 is equal to RO4. And this is exactly the same gain that we would get in a common source amplifier if it were actively loaded and the output resistance was RO and two of them in parallel. Okay, so what I'd like to discuss now are some differential amplifier non-idealities. All right, the first one is that differential amplifiers ideally should have none, but they do unfortunately suffer from common mode gain. We'll abbreviate this as AVCM for common mode. So in reality, current source transistors do not have finite input-output resistance, but have do not have infinite output resistance, but actually have finite R0. So this causes common mode gain. So for example, 60 Hertz signals in an ECG amplifier that are common to your electrodes may be amplified. And you really don't, at least traditionally, want that to happen. Okay, so let's go ahead and analyze this a little bit. What we can basically say is that when we're analyzing our circuit, let's just look at a resistively loaded circuit. Let's forget about the differential aspect. Let's only look at the common mode aspect. And I'm going to draw the circuit a little differently because we are looking at a common mode analysis. And furthermore, I'm going to assume that we're looking at the small signal model here. What we can basically see is that if we look at the common mode analysis, we have our two gates, V in CM. It's hard to draw right on the peripheral of my tablet here. And because we're looking at the common mode output, we can actually also tie the two outputs together. This is V out CM. Okay, so this is a symmetric circuit. We can this is RL, this is RL. We can replace that with a single circuit that looks something like this. This is RSS, RL over 2 because they're in parallel. This is V out CM, and this is V in CM. Okay, so here in this circuit, in this case, AVCM is equal to V out Cm over V in Cm. And I'm not going to go and derive this, but let's just come down to the final solution here. This is a very simple small signal model. You should be able to solve this pretty easily. Is equal to minus RL over 2 divided by 1 over 2 GM plus RSS. Okay. So in other words, this is not 0. Except in the extreme limit when RSS goes to infinity. And if that does happen, then this will go to 0. Okay. So the lesson here is that, we didn't include much non-ideality. We just said that bottom current source transistor has some finite output resistance, which we modeled as RSS. Okay. So the lesson here is that changes in common mode input can affect device biasing, which alters small signal gain. Recalling that GM is equal to ID over N phi T. And this can also affect output voltage swing. All right, so now this was a common mode gain, that is common mode to common mode gain, common mode at the input, common mode at the output. This is a problem, but if your next stage also is a differential amplifier, then it might have some common mode rejection, and this may or may not become a problem. What is more of a problem is a different type of common mode gain that is much more troublesome. This is what we call AV common mode to differential mode gain. Okay, so this is something we really don't like to see in our circuits. If devices or loads are not perfectly matched, if devices or nodes are not perfectly matched, then some input CM changes and some input common mode changes can lead to differential mode, to output differential mode changes. And that's really bad because once they're encoded in the differential mode, it's really hard to remove that later on. Okay, and so what I'd like to do is prepare a question, and this is an exercise that I would like you to at least try on your own prior to me giving the solution. And the question is: calculate the common mode, AV common mode to differential mode gain for a GM mismatch in some transistors. Okay, so in other words, what I'm saying is, let's say we have our differential circuit, differential pair. In this case, we'll do a resistively loaded differential circuit. And we'll have some finite output resistance here, RSS. And in this case, we're going to tie both inputs to the same voltage, VCM. Okay, so this is the same input. RLs are perfectly matched. These RLs exactly equal each other. This is V out 1, V out 2. This is GM 1 and GM 2. Now, nominally, they should be biased to have the same transconductance, but let's just say that for the purposes of this example, the W over L ratio or something of transistor 1 is a little bit different than transistor 2. Okay, so one hint that I'll give you for this problem is that we can say that ID1 plus ID2 is equal to Vx over RSS. That's a little hint that's going to help you with your analysis. So what I'd highly recommend that you do at this stage is pause the video and take a little bit of a time to try and solve this problem. Again, this is a type of problem that's very ripe for asking on a homework or midterm, and so please make sure that you do give this an honest effort. Okay, so hopefully you've paused it, and if not, well, you're not getting the most out of the lesson that you could have, but let's go ahead and write down the solution. So what I'm going to say is the current in that first device is going to be GM1 V in Cm minus Vx. The current in ID2 is equal to GM2 V in Cm minus Vx. Okay, so they're close to being equal except for the fact that these GMs are different. So then what we can say is GM1 V in Cm minus Vx plus GM2 V in Cm minus Vx is equal to Vx over RSS. That's basically saying that's doing KCL at this node. This current is plus this current is going to be equal to the current flowing through that resistor. Okay, so what we can do is we can rearrange that formula. We can solve for Vx. This is 1 over RSS plus GM1 plus GM2 is equal to V in common mode times GM1 plus GM2. Okay, now if we go ahead and solve for Vx, we get Vx is equal to GM1 plus GM2 divided by 1 plus GM1 plus GM2 times RSS times Vn Cm. Now, one thing that you might note is that this is a classic negative feedback equation, which is perhaps not surprising given that we are effectively doing source degeneration here, which is a negative feedback technique. So anyways, now that we have Vx, what we can go ahead and do is calculate Vout1, which is equal to minus ID1 times RL. That's equal to minus GM1 times Vin1 minus Vx RL. We can substitute Vx in there, and what we get is minus GM1 RL, all divided by 1 plus GM1 plus GM2 RSS times V in Cm. Okay, we can do something similar for Vout2. In this case, Vout2 is going to be equal to minus GM2 RL. There we go. Minus GM2 RL, 1 plus GM1 plus GM2 RSS times V in Cm. Okay, so what that means then is that Vout differential mode is equal to Vout1 minus Vout2, which is equal to GM1 minus GM2 all over 1 plus GM1 plus GM2 times RSS times RL V in Cm. Okay, so therefore, after all of this, we can say that the common mode to differential mode gain of this resistively loaded amplifier is essentially equal to delta GM, the difference in transconductance of our two elements there, times RL, divided by 1 plus GM1 plus GM2 times RSS. Okay. Now, if you did get that answer in your own analysis, congratulations. If you didn't, make sure you understand the steps that were taken. This is not a particularly hard circuit to analyze, especially given the hint that I gave you at the start there. But the actual answer here is actually pretty interesting. It basically says that if our transistors are perfectly matched, we get a 0 common mode to differential mode gain, which is great. That's the properties of an ideal differential amplifier. But that common mode to differential mode gain is linearly proportional to the mismatch between our two circuits. Now, fortunately, it is gained down by an effective gain of GM times the small signal resistance of that current source element, RSS here, and so usually that's a fairly large number, but it's not always as large as we would like. Particularly as we get into these biomedical systems, we actually really demand enormous common mode rejection ratio for these circuits to operate really well. So what we can say then is that let's go ahead and define what we mean by common mode rejection ratio, or CMRR. And what we typically mean by this is the differential mode gain of the circuit divided by the the common mode to differential mode gain. Okay. And so we know what the differential mode gain is. We know what the let's go ahead and do the differential mode gain for this particular circuit. I'm not going to derive it. I'm just going to write down the answer. It's RL over 2. And the reason we had to rederive this actually is because if we're assuming a non-matched condition, then what we say is it's GM1 plus GM2 plus 4 GM1 GM2 RSS, all divided by 1 plus GM1 plus GM2 RSS. Okay, so a familiar term on the denominator there. So we see then is that if we go ahead and take the ratio of this, CMRR is equal, and we simplify it, it's equal to GM1 plus GM2, these denominators cancel, plus 4 GM1 GM2 RSS, divided by 2 delta GM. Okay, which is roughly proportional to, if we assume that kind of this last term in the expression dominates, which it will over just GM1 and GM2, it's roughly equal to GM over delta GM times 1 plus 2 GM RSS. So in other words, it's the sensitivity of our GM circuits times some effective gain factor, and we can make this simplification if if we say GM is just equal to the average GM of the two devices. Okay. All right. So this is a problem, and as we'll see in biomedical signal acquisition, we really need this common mode rejection ratio to be enormous, higher than you could you even think would be reasonable. Actually, is often desired. Okay. So that's a really important thing for us to do as biomedical engineers, is to make sure we know how to design for very large common mode rejection ratio. Now, one other non-ideal effect that I'd like to briefly describe is offset. So due to mismatch in VT, W over L, let's try that again, W over L, mu Cox, etc., due to mismatch in these parameters between branches in our differential mode circuit, VID is equal to 0 if we apply 0 differential mode input. This does not imply that the differential mode output is going to be exactly equal to 0. And that's exactly what we refer to as offset. Now, typically when we talk about offset, we like to talk about what we call input referred offset, which we define as the non-zero VID that we need to apply that makes V out dm equal to 0. Okay, so in other words, what differential input voltage do we have to apply at the input of our circuit in order to make the output equal to 0? That's what we refer to as the input referred offset. Now, for resistively loaded op amps, we can say that the offset voltage, the input referred offset voltage, is roughly proportional. This is just a first order approximation to delta VT times theta times minus delta RL over RL plus delta W over L over W over L for resistive op amps. Or in other words, the resistively loaded amplifiers we were looking at before. And this theta term, what's that? That's where theta is equal to one of two things, VGS minus VT over 2. You can guess that this is going to be in above threshold, or it's equal to, and you might be able to guess this one as well, n phi t in subthreshold. So it turns out that offsets or rather offset limits precision in analog circuits. We can employ, and the reason this limits precision in analog circuits is, let's say our input referred offset voltage is 10 millivolts, and we're interested in measuring a signal at 2 millivolts. Well, if this is indeed within our input referred offset voltage, then we may not be amplifying it in the correct polarity. Okay, so there are a number of techniques we can employ. So we can employ techniques like auto-zeroing, calibration, etc., to reduce offset. So one quick and easy way to reduce offset is, let's say you have your primary transistors are your two input transistors there, and through fabrication, they may end up having different VTs or different W over Ls. What you can do is you could create a binary weighting of several different input gates on either side, and then do some calibration and select which pair of input gates that you would like to use such that the offset is actually minimized. There are a number of different ways that you could do calibration like that, as well as other techniques like auto-zeroing. We're not going to get into that right now, but just know that there are things that we as circuit designers can do to prevent that.